The extension of the Standard Model, SM, via Chern-Simons type interactions with a new massive vector boson, known as Chern-Simons bosons or CS bosons, is discussed. The minimal gauge invariant Lagrangian for the interaction of CS bosons with SM particles features 6-dimension operators and new dimensionless coupling constants. In the unitary gauge, the effective interaction of CS bosons with quarks of different flavors is considered, allowing for the construction of an effective Lagrangian and the computation of JV-scale CS bosons production in meson decays. However, divergences in the effective interaction with quarks of the same flavor or with leptons cannot be removed via counterterms. The renormalizability of the loop interaction is examined, concluding that divergences in the effective interaction with leptons cannot be eliminated. This indicates a potential limitation in the theoretical framework used to describe these interactions. The decay of the CS boson into lepton pairs and neutrinos is studied, focusing on the effective interaction with fermions of the same flavor. Diagrams illustrating the CS boson's decay into lepton pairs in the unitary gauge are presented, highlighting the necessity of considering loop diagrams involving W plus or minus, Z bosons, and photons. The vertex diagrams of the CS boson's interaction with vector fields of the Standard Model are detailed, described by equations 2.1, 2.2, and 2.3. The amplitude for lepton pair production via XWW interaction is computed using the alpha-Schwinger representation, resulting in equation 2.7. The propagators for vector fields and fermions in the unitary gauge are given in equations 2.5 and 2.6. The study emphasizes the importance of considering all corresponding diagrams to ensure the cancellation of divergences, aiming to understand the CS boson's effective interaction with fermions and its implications for the boson's lifetime and decay channels. The research paper examines lepton pair production in the context of XZZ and XZA interactions, depicted by diagrams A, B, C, and D in Fig. 1. The amplitude for lepton pair production via XZZ interaction is given by equation 2.12, involving the integral operator I micro ZA, which can be broken down into two parts, I micro ZA1 and I micro ZA2, as shown in equations 2.18 and 2.19. These equations involve integral operators lambda I, Lz gamma 0 and lambda I, Lz gamma 1, acting on functions d, Lz gamma, x, y, defined in equations 2.20 and 2.21. Similarly, the amplitude for lepton pair production via XZA interaction is given by equation 2.16, also involving the integral operator I micro ZA. The paper then focuses on combining the divergent parts of the diagrams in the direct approach, aiming to find conditions for the cancellation of divergences. It is observed that different lambda J1 operators contain equal divergent parts, as shown in equation 3.1, highlighting the divergent and finite parts of the operators. The authors extend the Standard Model by introducing a Chern-Simons type interaction, featuring a new massive vector particle, the Chern-Simons boson. The interaction Lagrangians contain operators of dimension 6, generating operators of dimension 4 after spontaneous symmetry breaking of the Higgs field. Focusing on the three-particle dimension 4 interaction of the CS bosons with vector bosons of the Standard Model, the authors analyze the divergent terms in the loop diagrams and show that the coefficients A, B, C, D, and E, given by equations 3.6, 3.9, cannot be simultaneously eliminated. The authors acknowledge the limitations of their approach, noting that the expressions for A remain unchanged under a shift of the integration variable, as encountered in the chiral anomaly. The paper concludes that the interaction of the CS bosons with vector bosons of the Standard Model is self-consistent only if the divergences in the effective CS boson interaction with fermions of the same flavors are eliminated by accounting for all appropriate loop diagrams, necessitating further investigation within the framework of a non-unitary gauge. Here is a combined summary of the 4 pages. The search for hidden particles and their potential implications for understanding dark matter, baryon asymmetry, and phenomena beyond the Standard Model are crucial in contemporary particle physics research. The SHIP, phasor, and dune experiments are discussed as prime examples of facilities that can probe the parameter space of new physics models, including the possibility of detecting JV-scale heavy neutral leptons. The SHIP experiment at the CERN SPS is designed to search for hidden particles with lifetimes above 100 picoseconds, while the phasor experiment is a dedicated search for long-lived particles in the very forward region of the CMS experiment. The dune experiment, with its focus on long-baseline neutrino physics, also has the potential to discover hidden particles. Theoretical frameworks for understanding hidden sectors, including the NUMSM model and the role of axion-like particles, are essential in this context. The concept of paraphotons, introduced by Okun, is also mentioned as a possible hidden sector particle. Furthermore, anomalous U-1 extensions of the Standard Model are explored, focusing on the theoretical framework and phenomenological implications. Generalized Chern-Simons terms are highlighted as essential in cancelling anomalies in these theories, while the effective theory of anomalous U-1 extensions is discussed, including the role of Stuckelberg vector bosons and their interactions with matter fields. The connection between anomalous U-1 symmetries and the Green-Schwarz mechanism is also covered, as well as the constraints on light vectors coupled to anomalous currents and the production of Chern-Simons bosons in decays of mesons.